Thank you. Thank you very much, and thank you for allowing us to present our work. I'm Petrus Aejmelaeus-Lindstroem. I'm from Stockholm originally, and I'm a researcher at Grammazio Kohler, so I'm doing a PhD about jammed architecture structure. So basically what we will present now is what I'm working on.
I'm Andreas Thoma. I also work at Grammazio Kohler Research, and I'm currently a research assistant at the chair, but I will be pursuing a PhD. And I joined this project for part of it. So it grew out of research. We had the rock print exhibition grow out of the research project, which Petrus is doing. So I was part of this project for, I think, 5 months approximately, or 6 months. So I'll hand it over to Petrus to introduce us to the research.
So basically the topic is called jammed architecture structures. It started with the idea of building structures out of granular matter. So basically by compressing together granular matter that can interlock and behaves like a solid. And when you release the confinement, or if you take away the force that holds it together, it becomes loose again. So you can kind of see the initial idea was this diagram. Somehow we want this magical material. And the first experiments we did was with cornflakes. Just, there's a lot of friction, it was kind of flat, so we thought that maybe by adding it. And what's interesting about this picture is that it's just a tube that we had cornflakes in, and then we were moving the tube upwards. And by doing this, cornflakes just goes out and goes everywhere. But by adding a load on top of it, it becomes stiff, and it somehow works. So this, we have a load inside the tube, a PET bottle with half a liter of water, just pressing down, and then it kind of works. So we did a lot of small experiments to see, okay, where could this go? What happens if we increase the force? And cornflakes is not really a construction material, so we're thinking, how can we scale it up? And we started to look at gravel. Can we use some kind of rock or natural stone to get the same phenomena? And what I did was that I started to layer gravel with very, very thin paper. And we got these very slender columns, and we kind of, at this point, got the feeling that this is the right way to go, that we can figure out something that will work. So we built a test rig. It's basically just an axis that's one-dimensional that we can just compress. We can control the load we're pushing downwards, and then we could have different samples inside. So what we did was that I recreated this gravel and paper, but I used a different membrane, and we could have loads up to 100 kilos on this little sample. It's basically a 30 centimeter. But then from this, we started to think that maybe we can have something that we don't have to layer. Maybe we can just mix a material, use some materials that we can get the same behavior, but without this layering part. So we started to do a lot of tests. And in the beginning, we just mixed different things, some change and some cork. And then we figured out that that stones and string works very well. So we had this chain, this kind of Swiss chandelier chain from Cope. And we had some interesting results, but then when we started to use string instead, we got this very good results somehow, very interesting results. So here's basically the test we did. And here you can see the gravel and string, which was very, very interesting when we started to get the results. And we could do columns of a slenderness ratio of 1 to 12. So very thin, slender columns that could sustain 50 kilos, a bit more. And based on this, we started to look at how can we fabricate this because basically we were filling a mold before, and we were interested in how can we fabricate something without this mold, and how can we also control the geometry. So the idea was that we would want a process that we can control the jamming or this, the geometry we do with robots. So we could have a digital control of the... So this was a very early state that we did somehow like a slip casting. This mold we're using had a slight angled walls, and we were moving it manually upwards, and then the robot was just placing the string inside. And this was kind of a steady process. It almost always worked, and we could repeat the experiments. So, but using this method, we were trying different proportions of gravel, different size of gravel, mixing small and larger gravels, different amounts of string, and proportions between the gravel and the string, just to start to understand how it works. And at the same time, we got an idea of this. Basically, the string is deciding where the material holds together and where the material doesn't hold together. That maybe we can use a process similar to powder-based 3D printing, that we put a layer of gravel, then we put a layer of string, and then we put a layer of gravel. And by doing this, we could somehow 3D print small structures, even a wall with an opening. Yeah. And then what we wanted to do was to very quick see, can we scale it up? Because this was done in a, I think this is 30 by 40 or something like this, centimeters, so very small samples. So very quickly we did a test with a bigger robot, and now we placed the string by hand, we placed the gravel by hand, but we were guiding the mold with the robot. And we can also see here in the picture Skylar Tibbets that was collaborating with for Rockprint for installation that we will talk about. But yeah, so you can see this hands-on also in the process. And this way we could see that we can actually do structures that are big somehow, or in architectural scale. And now I will let Andreas continue presenting.
Yeah, so we were invited to submit a project for the Chicago Architecture Biennial, which was in 2015. It was the first time that they were doing it again. I think it was originally in the 70s, it was stopped, and then they decided to reactivate it. So we decided to then submit a project coming out of this jammed research. So this is when I joined the project, which is now Rockprint. And when I joined, I wasn't quite convinced this actually works. That you can just, with string and rocks, you can create something vertical. It's quite counterintuitive. So this was actually the first test where I was also part of the project. And here because of the load constraints that we had in Chicago, we were asked to exhibit inside a building in the center of the space. We decided to use a different material than rock. So we actually decided on Mesapore, which is it's a foamed glass, which kind of looks a bit similar to river stones, this kind of aerated stones, and it's about, I think it's about 1/8 of the weight that you usually have with rock. And yeah, so as a next test, we just stood on it to see if that actually works, and
to be convinced.
Yeah, to be convinced, and it's relatively stable. It's a little bit spongy, but you can kind of add as much load as you want. It won't immediately break. It will just compress somewhat. So this test was made by hand, just to kind of get a feeling for the material properties. And we then proceeded to do various tests to figure out what this material system can actually do. And at the beginning, we actually had quite a few failures, so we were a little bit nervous what we can submit at the end. And at the top left, you can see the first experiment we did, which was at large scale using the robot. And that was a complete failure. When we took the formwork away, it already kind of destroyed half the structure, and then at the end, it all fell apart. So we also realized we have to do this decasting outside. We can't do it in laboratory space because everything just gets covered in dust. So we had to design a system where we could always bring the things outside for decasting, even though the robots we were using were inside. The next two on the left, we optimized a few things. But then again, it also failed. When we decast it, it tipped over. So then we were getting very nervous, because at this time we had already agreed to submit something in Chicago using this system, but we weren't quite sure how. So to be a little bit more on the safe side, we actually just decided to do a rectangular volume, because if that doesn't work, then we're really in trouble. And that's when we also introduced packing. So every 5 layers of fabrication, we would condense the material a little bit by jamming it.
With the concrete compactor.
Exactly. And that then worked perfectly well. So after that, we kind of gained a little bit of confidence again and started making cantilevers and holes and all this kind of stuff. So yeah, at the bottom in the middle picture you can see it's 2 slender legs, but you can still stand on top without a problem. And in the next video, we wanted to see how stable is this system. So if we actually pull away one of the legs, for example, what happens? So actually, funnily enough, it just kept standing, which we weren't expecting. Well, maybe Petrus was. I wasn't expecting it. But then obviously when you pull away the second of 4 legs, then it doesn't work anymore. And because we're building it layer by layer using one continuous string, we wanted to see, okay, at a later stage, if one was to separate the 2 materials back into their raw state, how could you do this? So we just had a look at just pulling the string out. So that was a really good way, a very quick way of separating the 2 materials so we could use them again, but it also had quite a nice, I guess, performance effect, which we then wanted to implement in Rockprint later on. These are the first large-scale test we did of Rockprint. We first fabricated it in Zurich because we wanted to see, does it work? We wanted to see what issues we would have with logistics. And as I mentioned before, in Zurich we had to fabricate it inside and then bring it outside. So here you can see the I think 4 meter high formwork being taken outside, and then finally being decast outside. So we would, again, everything was a little bit unknown, so we were on the safe side. We decided to attach the formwork to some weights so it can't tip over no matter what's happening. But actually, when we started decasting, we realized it's extremely stable. Like even the flush side doesn't even fall off, even though this part didn't actually have any string. So just through the packing, it was also being held a little bit in place. And here you can see the process of decasting. Because it was quite dense, we then had to somewhat sculpt away the surface. So it was quite easy to remove. The bits which had string, they were then more difficult, so it made it very easy for us to just kind of remove all the excess material.
And basically we just had to touch the surface and then just came in like avalanches of...
And we were also doing it with a 4 meter long stick at the beginning, and then we kept getting more confident and closer to it, which maybe isn't such a good thing, but it was fun. So yeah, that's about the last scratching away. Then, yeah, we were immensely relieved after that worked. So in this test, we were trying to see again the limits. How thin can we get the legs? How much cantilever can we get on the top? Because we really wanted to show the boundaries of what the system can do. Some more photos outside. And then this pile at the bottom, we weren't sure if that's also kind of supporting these legs. So we actually removed the pile, and there you can see how slender it is at the bottom. And again, as always, we wanted to see how it breaks. Go on, hit it again. I think we were discussing how to then hit it, it's just like hit it till it breaks.
Was it the cucumber test?
Yeah, we also did so this was the first one that we made and destroyed. And we weren't sure exactly how liability would work with this thing because no engineer would sign it off officially. So with this, it was quite good because we could see it doesn't just tip over, it kind of collapses inside itself. So the safety distance you would require wouldn't be so big. But then we talked to engineers, Walt Galmarini, their office. We invited them for a meeting to talk to us about this, and they said there's no way they will ever sign this off, but they can give us some advice as to how to proceed with it. So we then also did a watermelon test. We put some watermelons around it and then made it fall on top of the watermelon. And we didn't think about this, but we couldn't actually find them very easily. So we then, similar to an avalanche victim or something, we had to kind of probe the pile until a wet stick came out, and then we knew we found the watermelon. And the watermelons, apart from the stick damage, they were actually fine. So we then had a bit of a better feeling.
Because even if it's a lightweight material, this is 3 tons, the whole structure, so it's still quite a heavy weight to. So I want to see how it behaved.
And they then also advised us in Chicago we should just hook up some webcams. We should monitor it over time and see if it's slowly shifting. See if it's if it's shifting over time, then it would be a big issue. But we noticed we fabricated one of these and we left it outside for I think 2 or 3 months. It was absolutely fine, even though it had been in the storm, rained on, everything. So we had quite a good feeling.
The wind was the worst because the material on the top surface was just spreading away with the wind.
Yeah, so now actually to Rockprint, to the Chicago contribution.
So basically we actually built it 2 times, exactly the same structure more or less, because there's 2 reasons why it looks like it does. The first reason was because it's 4 meters high, so basically visitors, in case they would touch the structure, they would touch it here, not here. And so this is the most exposed part, and our structure actually becomes stronger the more load there is on it, until a certain point. But therefore we made the structure so we would have more mass in the top, and basically increasing the force on the legs, and making it more stable. So basically by creating this inverted logic column that is bigger in the top than the bottom, we actually create something that was more stable than the opposite. So if the legs would have been in the top, they would have been very unsteady because of the lack of weight. And we also built it 2 times because we couldn't simulate how the material behaved, we couldn't simulate the density. So what we needed, because basically how the pattern works is that it circles, that is reinforcing the gravel. And these circles, if the string is too dense, if we have too many of them, the force is not transferred so well between the particles, because basically it becomes like a sponge. There's too many soft material in between. And if we have too little string, then the gravel just falls out. So what we were looking at when we were building the samples was to see how can we create the most articulated geometry, how can we make sure that we really get something nice to look at while still managing to spread the string pattern. And the other challenge is that in the bottom, as you can see, it's basically just 4 circles in each foot, leg. And in the top we have a couple of hundred. And the problem is every time you add a new circle to the system, you have somehow to find a place to put it. Because if there's nothing inside the structure, so if you just add a circle and suddenly increase the the amount of circles, the material would just fall out. So basically it needs to be continuous and distributed. So we worked quite a lot with figuring out how can we distribute this pattern, how can we maintain the same surface quality while allowing for changing the geometry. And so this is also where the computer and the robot really comes in, because this is not possible to do by hand. We can't draw the pattern by hand. We need to be able to analyze it and to produce it. And at the same time, we can't place the string by hand if it's constantly unique. We can't make a template for every layer. So basically the string is the smart part of the structure. And then the other part was that we were pouring the gravel by hand. We were placing the gravel by hand. But the only part there that was important was to have a consistent volume. But the placement of it was already defined by the mold. I will show it later. But basically, so we aim to use the robot only for the part that we couldn't do by hand, to really emphasize on the interesting part of the pattern, and the rest of the structure we would do by hand, because we could do it better by hand. We were faster by hand. We were several people, so we could work together. What we also very early knew was that we couldn't prefabricate this mold that we showed earlier on a slide, this yellow box, and ship it to Chicago, because we had no clue how the material, how the structure would change during transport. How much the material would compact, would it deform, would we suddenly have a different geometry, would you have too much overhang, So we had to ship the robot. And just as a small parenthesis, shipping the robot is not so hard, but wiring the robot is quite tricky. I mean, there's a different frequency of the current, and this is quite interesting, actually, how tricky something so simple can be. So we shipped the material also, and what's quite interesting was that when the material had arrived, they had compressed by 20%. So basically, because super high friction is, you can touch it later, and basically due to the friction and, I don't know, the rocking of the boat, the material changed. So we had to readapt the pattern actually when we arrived to Chicago to the size of the new particles. But this is the setup. So it's a robot. So basically it's a 2-axis setup with a robotic arm mounted on it. Very lightweight arm. Arm plays the string, and the axis setups allows the robot to move wherever we want it to be. So this is clips from the movie. We'll show the whole movie in case you haven't seen it later. But basically here you can see the pattern in the middle of the structure, and the robot slowly extruding the string. And it was basically 40 hours of machining time behind the structure. So the robot was working for 40 hours, basically non-stop. And after the robot had placed the string, we just poured out the gravel. And as you can see, it's very easy to do it by hand. You don't need the robot to do it. And then we dismantled the box, and we had the same phenomenon as before. So we had to brush it again. But you can see it's really just touching the surface is enough. So it wouldn't be a risk that we would actually sculpt it out another geometry than planned, because like this was quite stable. And now we were really, really happy. So actually it was almost 500,000 visitors at the Biennale also. So we had a lot of people there, and a lot of people saw the project. And then just a close-up on the surface. It has something of magic with this, because this material has this super high friction that you can really see how the particles are somehow flying. But there's no glue, there's only string and stone. And we were thinking that we would show the whole movie now. It's 5 minutes. I don't know if you all have seen it, then we can skip it. But then tell me. So if you get annoyed. Yeah.
Yeah, I'll say so. So when we went to Chicago, for example, the simple issue that the States still has a different power system than the rest of the world created quite an issue with the robot. So we needed to change the frequency from 60 hertz to 50 hertz. So we had to rent in this specialized equipment which was actually nothing other than a electrically powered power generator. So you would be spinning a part, which is spinning another part, which is then generating electricity again. And we basically treated going to Chicago like going to the moon. So we took everything with us, basically everything apart from electricity. Because we didn't want to rely on any of the infrastructure there. We just wanted to be able to guarantee that we can get it to work. So we even took our own pallet jack, we took our own material, and here you can see all these bits and pieces being activated and turned on. And the robot waking up. So this is the leg which Petrus mentioned before. So it's just 4 little circles, and you kind of mark the beginning of the rock print.
Actually, it's double along the edges to define them.
Right.
To a more defined geometry. That's also why the process were quite slow. Was because it was very important the string is exactly where we think it is. So we tried different techniques, for instance, by shooting string with air pressure, but then the turbulence made it a bit too wobbly. We couldn't have as precise surfaces.
So I think we spent pure production time, I think it was about 5 days to finish fabricating it.
Yeah, including removing the molds.
Yeah.
Here also, by releasing the mold, it was quite important that we released it symmetrically, because if we would release it faster on one side than the other side, it was a risk that the structure would settle and it would be slightly leaning or not so precise. Yeah. For scale.
So later on we took the photo because I'm in it and I'm a little bit shorter, so it looks a bit bigger. And these were the webcams we were using to monitor the structure.
And there was no movement, no change.
Then when did we go? February, January. In January we flew back at the end of the exhibition to then to disassemble it.
This is it was basically a string network of 4 strings. So in each leg had one continuous string, and then they were all connected in the end. So we started with the low speed to see. It was a very, very dusty process.
And to do this, we also had to mount some hooks onto the ceiling to be able to make the string go up and then down again. So you can, if you look at Petrus very closely, you can see him, he's a little bit nervous because he's wondering whether the hook is going to come down.
It's 10 meters above. Massive steel structure. It's a bit. Yeah. And we had a very nice gradient in the end on the floor about how the particles had spread out. It took 2 hours roughly to unwind.
So 5 days to assemble it, 2 hours to pull it apart.
Now I got tired by the stress.
It's not very heavy, and we can show you later on.
Some of the hook above those.
The hook, yeah, that one, maybe.
So the string broke in the middle, so that's why we had to have this fishing rod technique. But in the end, we completely recycled it. So the spool of string still exists in somewhere in the basement, I think in Chicago. And the gravel is used for landfill in the park somewhere. So yeah. And then, yeah, just quick. Rockprint got awarded the Starts Prize, so it will be at Ars Electronica in Linz later this year. And just as a very, very small teaser, what we're doing right now is what we try to do is basically continue with the same technique or the same material principle, but without the mold, without the box. Because if we want to print a house, we don't want to have a bigger box than the house and then excavate all the excess material. So it's just a very, very quick documentation of the principle. So right now what we're doing is that we're just placing string in the air. How do we jump?
Go across here, skip.
I'm going to skip a bit.
How you do it?
So the string we all recognizes, and then what we do is that the robot has a soft mold, which we place a defined amount of aggregates, and then maybe the most funny part is that we're packing it, and so this is what we're looking at right now and getting more refined. So this is an early prototypical stage, and yeah, basically this is the surface quality we're getting. But the big difference here is that we're using stone instead of this lightweight glass foam. But there's still something magic with the surface, I think. You still get the feeling that there's more stone than string, which it is in all senses. But yeah, thank you very much for allowing us to present our work.